So quick review here. Yesterday, we were talking about latent heat, which is far more important than whatever it is the two of you are talking about. Yeah. Okay. So we were talking about latent heat. We're talking about how that is the energy required to change the state of a material, in this case, water. Okay, whether it's melting the water, or whether it's vaporizing the water, or whether it's condensing steam, or freezing water back into ice. Okay, that kind of stuff. All of those are state changes where what kind of thermal energy is changing? Nope, other way. Potential. Okay, if I'm changing the kinetic thermal energy, then the temperature will change, because temperature is a measure of the kinetic thermal energy. Remember, we talked about yesterday how it measures how often the particles hit the thermometer. That's what transfers the energy to the thermometer and makes the alcohol or whatever is in it rise. Okay, so it's measuring the kinetic thermal energy. So if there's a temperature change, then we use E equals mc delta T to calculate how much energy is required. Okay, but if there's no change in temperature because the water is changing state in some way, then we have to use one of the two latent heat formulas. That could mean that we're using E equals MLF or E equals MLV. Okay, which one do I use if I'm talking about how much energy would be lost when water freezes into ice? MLF, right, melting, freezing. Okay, if we are looking at how much would be involved in vaporizing a bunch of water, then it would be E equals MLV. All right. Now, we talked also about how these state changes require lots of energy. The latent heat of fusion of water is 333 joules per gram. That means if I have 1 gram of ice, okay, and we talked a bit about this yesterday, which would be about the size of a raisin, it would take 333 joules worth of energy to melt it in my hand. Okay, which, as we said yesterday, is why your hands get cold if you're making a snowball with your bare hands. Okay, you're melting a lot of ice, it takes a lot of energy from your body to do that. Okay, and even more than that is the latent heat of vaporization. It takes 2,260 joules per gram worth of energy in order to evaporate water. Okay, so if I have 1 gram of liquid water, okay, that's 1 milliliter. Okay, not very much. It takes 2,260 joules worth of energy to evaporate that away. Okay, and that's why sweat works. We talked about that yesterday. Okay, when we sweat, the water evaporates off of our bodies, taking energy from our body to do it, making us feel cooler. Okay, is that ringing a bell from yesterday? All right. The other thing we looked at was the heating curve of water. So this thing here. Okay, so down here in this first section is where what is happening? Raising the temperature of ice. So this flat line here occurs at 0 degrees Celsius, and this flat line here occurs at 100 degrees Celsius. So during this flat line, ice would be melting or water would be freezing. Okay, during this part here, okay, the horizontal, or sorry, the diagonal part, we would have water changing temperature, and then we would have water evaporating during the horizontal part at 100, and then steam being heated in the diagonal part after that. So anywhere where the line is flat, we're going to be using one of these two formulas. Okay, for this flat part at 0 degrees, okay, we use E equals MLF. For this part up here, we use E equals MLV because it's vaporizing up there. Everywhere else where the line is diagonal, we're changing the kinetic thermal energy, so we use E equals mc delta T. All right. Same here. What do I have to be cautious of during each one of those parts where I use E equals mc delta T? Right, know exactly how much the temperature is changing by in that section, not over the entire question. Okay, and the second thing is C the same for each one of those parts. Okay, water has a different specific heat capacity for each state. Right, so we have to use the specific heat capacity of ice if we're below 0. Okay, if we're between 0 and 100, we have to use the heat capacity of water, and if we're above 100, we have to use the heat capacity of steam. Okay. Everybody all right with that? All right. So now this is, obviously this is the heating curve under ideal conditions. Okay, under ideal conditions, which would be, 1 atmosphere of pressure, things like that, water boils at 100 degrees Celsius. Okay? Does water always boil at 100 degrees Celsius? No, it doesn't. In fact, here, okay, water boils at around like 96. Okay, maybe even a little lower than that. Okay, why is that? Yeah, we're at altitude. There's less atmospheric pressure here than there would be at sea level, where the atmospheric pressure would be exactly 1 atmosphere. Right, so water boils at a much lower or a lower temperature here. Okay, if you're like climbing Everest or something like that, like when those guys are making their food, they make soups and stuff like noodles and things like that. Okay, they take the snow, they melt it, and they boil it on their little stoves, but they have to eat it while it's boiling because it boils at like 60 degrees. Okay, because they're so high up in the atmosphere that there's so little atmospheric pressure, water boils right away. Okay, it's also why they have to be constantly drinking water because water evaporates off of them and out of their respiratory tract and stuff way faster than it would at normal altitudes. Okay, so they can get dehydrated really quickly and things like that. So atmospheric pressure plays a big role in what the boiling point and, okay, to an extent, freezing and melting point of water or any material would be. Okay? This is why you can also use a pressure cooker. If anyone has like an Instant Pot, okay, at home or a pressure cooker, okay, you put the lid on and it'll build up a bunch of pressure so you can get liquid water to stay liquid up to like 140, 150 degrees Celsius, which means you can cook stuff a lot faster, okay, because you put it under pressure and it won't boil off. All right, so let's have a look at this example question here, because this is kind of what we're going to be looking at today. How much energy is needed to heat 500 grams of water at 6 degrees Celsius into steam at 170 degrees Celsius? All right, so yesterday we went over a 5-part example of a problem like this. Does this question have 5 parts? How many does it have? 3. Okay, so what we want to do, we said yesterday, is mark the starting point. So there's about 6 degrees Celsius, and the ending point. There's about 170 degrees Celsius. Okay, which means I have 1 step, 2 steps, 3 steps to do. All right, once I've identified how many steps, then I'm going to write those down below. Okay, so now that I have identified how many steps I have to figure out what's happening in each step. So in step 1, what am I doing? I'm doing E equals mc delta T because I'm changing the kinetic energy and thus the temperature of the water. All right, so I will use E equals mc delta T for step 1. Okay, so that's going to mean a mass of 500 grams. What C am I using here? Which specific heat capacity should I use? Water, yeah, which is 4.2, right? Okay, 4.2 joules per gram degree Celsius. And how much am I changing the temperature by? 94 degrees, right? I'm going from 6 to 100. All right, so that's my first step. Not 96. Okay, so we got 197,400 joules. All right, so that's the first part. Okay, what's going on in step 2? Right, E equals MLV because now the water is boiling and it's vaporizing. So E equals MLV. All right, so that's going to mean, again, 500 grams. That's not going to change. Okay, times 2,260 joules per gram. All right, so we're looking at 1,130,000 joules. Is that a lot? Yeah, it is. Okay, step 3. I now have steam at 100 degrees. If I keep adding heat, what's going to happen to the steam? It'll heat up, it'll get hotter. Okay, that means that I'm changing its kinetic thermal energy and thus changing its temperature. So I use E equals mc delta T. I still have 500 grams, but now I'm heating steam, which has a different heat capacity, 2.02, and I'm going to change its temperature by how much? 70. All right, so we're looking at 70,700 joules. So obviously, the biggest part of this whole change is going to be the changing of water into water vapor, right? And again, we talked about how yesterday, I mean, that's 1,130,000 joules, and we are talking about a half a liter of water. In just 1/2 a liter of water, there's that many joules of energy stored as latent heat. Okay, imagine when a warm air mass carrying millions of liters of water moves from one place to another. How much latent heat does that bring with it? Okay, so it's a really important energy transfer mechanism. Okay, what do I do with those three numbers? Add them up. Okay, then I've got the final answer. Okay, so we're looking at 1,398,100 joules as our final answer for that question. Okay, so again, we don't have to manipulate any formulas. We've just got to plug in numbers, okay, and then at the end, add them all together. They're not mathematically difficult problems. We just got to make sure we get the right numbers in on the calculations, right? So what I want you to do is work on a couple of those from the sheet I had up here yesterday. We got to question 6 yesterday, I think. So I want you guys to try 7, 8, 9. Actually, I'll put up the other sheet here so you can see them all. All right, so let's have a look at number 7 here. So we're trying to calculate the total heat required to melt 0.1 kilograms of ice, which is how many grams? 100. Okay, so the first thing is you got to convert it to grams, right? Everything else is in grams. The specific heats are joules per gram degree Celsius. Latent heats are in joules per gram. Okay, so we're going to draw our heating curve of water here. We're required to melt 1 kilogram of ice at -20. So I'm starting down here at -20, and I'm going to here. It tells me the final temperature will be 0 degrees Celsius. So that is only 2 steps. All right, so in step 1, I'm going to have E equals MC delta T, because I'm heating up the ice. And then in step 2, I'm melting the ice. So that'll be E equals MLF. Okay, so we're going to have 100 grams times 2.116, the specific heat capacity of ice. And I'm changing the temperature of the ice by how much? 20 degrees. I'm going from -20 to 0. All right. So when we do that, okay, we should have 100 times 2.116 times 20 degrees, okay, is 4,232 joules. Okay, and then for E equals MLF, it's 100 grams times 333. Okay, we should be 33,000 joules. Yeah. Yeah. Sorry. 33,300, not 33,000. Okay, 300 joules. All right, so we add those two together, and we'll have our total 37,532 joules. It's the specific heat capacity for ice. It's on the table there of specific heat capacities. Oh, you know what? Okay. How many people are using the one on the back of their periodic table? I didn't realize that someone had altered my periodic table. That's what happens when you have a shared document and you don't keep up with what people are doing. Okay. Yeah, so if you use that number, but your methods are fine, you're good. It should be 2.116 though, guys. Okay. Have to make sure I double check that before the final exam. Make sure that that's right on the final. Okay. How about 8? Yeah, I can go over 8 too. All right, so calculate the quantity of heat needed to convert 0.05 kilograms of ice initially at -10. All right, so let's draw the heating curve. That's always the first step. Okay, so I'm starting down here at -10, and I'm getting to water at 80 degrees Celsius. So that would be right here, because obviously water boils at 100, so I'm not getting all the way up to the horizontal line. So that'll mean 1, 2, 3 steps. All right, so in step 1, I'm heating up the ice. So that'll be an E equals mc delta T problem. Right? Then I'm going to melt the ice in step 2. And then I'm going to heat the water. All right, so there's my 3 mathematical calculations I'm going to have to do. Okay, so the mass here, 0.05 kilograms, is 50 grams. Right, so a little bit of metric conversion stuff here. So 50 grams times, again, 2.116 joules per gram degree Celsius for ice. Okay, and how much am I changing the temperature of the ice by? Just 10. Right, it's going from -10 to 0. After 0, I don't have ice anymore. All right, so I have that step, and then I have the equals MLF, which will be 50 grams times 333 joules per gram. Okay, and then I'll have E equals MC delta T, 50 grams times now water, 4.2 joules per gram degree Celsius, and I'm changing the water's temperature by 80 degrees. All right, so I can just punch these in on the calculator here. So we'll have 50 times 2.116 times 10 plus 50 times 333 plus 50 times 4.2 times 80. All right, 34,508 joules. Okay. Making sense? Is it the metric conversions that we're getting us? Or was it the wrong specific heat capacity for ice? Okay. Water's wrong too on there? Okay. Okay, I will change them so that the one I give you on your final exam is right. Okay. Thanks for catching that. Yes, you'll be given all of those, yeah. Okay. Usually I just give those numbers in the question itself, but if there's a data sheet with contradictory numbers, I need to make sure I fix that. So. All right, keep her going then, guys. Okay, so the minimum amount of heat required to vaporize 4 kilograms of water at 0 degrees Celsius. Okay, if I just want to vaporize it, it doesn't mention anything about heating up the steam afterwards. Okay, on my heating curve of water, I'm going to start here at 80 and end where? At 100, but at the beginning of 100 or the end? At the end. I just want to vaporize it. I don't want to make the steam any hotter after that. Okay, so this is going to be a 2-step problem. All right, so in step 1. In step 1, okay, I've got 4 kilograms of water. How many grams is that? 4,000. All right, so I've got 4,000. Sorry, I should write the formula here. What am I doing in step 1? Am I evaporating or heating? Just heating. All right, so I'm changing the kinetic thermal energy. Okay, so that'll be E equals mc delta T. The mass is 4,000 grams, so this is 4 liters of water. Okay, times 4.2 because it's water. Okay, and then multiply that by the temperature change. How much am I changing the temperature by? 20. I'm going from 80 to 100. Right, so just 20. All right, so for first step there, 4,000 times 4.2 times 20 degrees gives us 336,000 joules. Okay, follow me on that part? Amanda, is that? Okay, but make sure you hear the instructions too, okay? All right, so for step 2, okay, in step 2, now I've got the water to 100 degrees, so now it's gonna start to boil off, okay? And when it's boiling off, its temperature doesn't change, so I have to use E equals MLV because I'm vaporizing the water in this step. Okay, so I take the mass, 4,000 grams, and I multiply it by the latent heat of vaporization, 2,260 joules per gram. All right, so we got 4,000 okay, times 2,260. All right, so we got 9,040,000 joules. Okay, so when this is all said and done, that's going to be 9,376,000 1,000 joules for a total. All right, so the set of steps we always want to walk through on a situation like this is to draw the heating curve of water first and mark on it our start and end points. So I started here at 80, okay, and I know that that step will end at 100 because then the water will start to boil off, which is the second step. All right, so just identify them on the heating curve first, okay? Then look to see if there's any tricks in the question, like they gave you the mass in kilograms. That's about the only trick there can be. Just double check that you're not using a number that's 1,000 times smaller than it's supposed to be, okay? And then it's a matter of just, okay, I got to identify in all the diagonal ones, I use E equals MC delta T. In all the horizontal ones, I'm using one of the latent heat formulas, right? So you can maybe just like give yourself a cheat sheet, okay, that just was kind of like what we drew at the beginning of the day here, okay, where I said, all right, in this part here, you always use E equals MC delta T. In this part, you always use E equals MLF. Here you use E equals MC delta T, and so on until you kind of get the hang of it, right? Then you don't need your cheat sheet anymore because obviously you won't be able to have that on a unit exam or final exam, okay? Incidentally, the heating curve of water is not on your formula sheet, okay? It is expected that at this point in your life, you know that water freezes at 0 and ice melts at 0, and that water boils at 100. Okay, we just expect that at this point you know that. All right, so the heating curve of water is nowhere in your givens, it's nowhere on your periodic table, nothing like that. We just expect that you know that shape. Okay. All right. How are we doing with how many people have done number 10? Okay, do we need to go over that one too? Yes. Okay. All right, so in number 10, okay, we have looking for how much heat is released. So this time we're actually cooling the stuff off and energy is being given off. It doesn't really change what we do, okay? So we have 150 grams of steam at 130, and it's condensed, then cooled to 30 degrees Celsius. All right, so if I draw my heating curve of water again, okay, I'm starting up here at 130, and I'm going down to here at 30 degrees. Everybody with me on that? How many steps is that? 3. I have to cool the steam to 100 so that it can condense, which will be that step, and then I've got to cool the water from 100 to 30. All right, so that'll be 1, 2, 3 steps. All right, so in step 1, okay, I'm changing the temperature of the steam. It's one of the diagonal parts. On all the diagonal parts, I'm changing the kinetic thermal energy and thus the temperature. So I use E equals MC delta T. All right, so we have 150 times the specific heat capacity of steam, 2.02, okay, times, how much am I changing the temperature of the steam by? $30 degrees. Yeah, I'm bringing it from 130 down to 100, 30 degrees. And guys, that's often the part that trips people up. The most common mistake in these kind of questions is putting the wrong temperature changes in. Okay, you just have to read the question carefully, okay, do the right subtraction operations. All right, so that's our first step. In step 2, we're going to condense the water. Okay, condensing and evaporating, the formula is the same. Okay, it doesn't change what we do in terms of that. All right, so it's just going to be E equals MLV. The mass is 150 grams times 2,260 joules. And then in step 3, I now have cooled this, I've condensed the steam, now I've got to cool the water, so I'm changing again its kinetic thermal energy because it's one of the diagonal parts where I use MC delta T, 150 times 4.2 times the temperature change. How much am I changing the temperature of the water by? 70, because I'm going from 100 down to 30. Okay, so the temperature change is 70. All right, when we add those up, we should get 392,190 joules. All right. Everybody all right with that? All right. You can. Okay, keep working on it there, guys. Okay, so number 11 is a big one because we start out with steam at ice at minus 40, and we're going to steam at 160. Okay, so we've got basically the entire heating curve being involved here because we're starting down here at minus 40, we're going to 160 degrees, which is way up there, so we're doing all 5 steps. All right, so in step 1, I'm taking ice at -40 and heating it to its melting point, which is 0. Okay, so that's going to be a temperature change one, so E equals mc delta T. Sorry, that's step 1. Okay, and that's going to involve us taking the 80 grams worth of water, or worth of ice, sorry, times 2.116, the specific heat capacity of ice, and I'm changing its temperature by 40 degrees Celsius. All right, so 80 times 2.116 times 40 gives me 6,771.2 joules. All right, step 2. I've got the ice to 0 degrees Celsius. If I keep adding heat, the ice will melt. Okay, and when it's doing that, okay, we are looking at a change in potential thermal energy. That'll be E equals MLF. So that will equal 80, the mass, times 333, the latent heat of fusion of water. And that'll give us how much energy is required to melt the ice. So 80 times 333 is 26,640 joules. All right, so that's step 2. Okay, now after step 2, I have liquid water at 0 degrees Celsius and I keep adding heat. What'll happen to it? It'll raise its temperature, right? So that'll be a change in kinetic thermal energy. It's a diagonal part of the heating curve. So we use E equals mc delta T, 80 grams times now the specific heat capacity of water, 4.2, times the temperature change. How much am I changing the water's temperature by? 100 degrees. I'm going from 0. I'm on my way to 160. It's only liquid water till it gets to 100. So changing it by 100 degrees Celsius. Okay, so 80 times 4.2 times 100. So we're looking at 33,600 joules. All right. At the end of that step, I now have boiling liquid water. If I keep adding heat, the water will boil off, and that means the temperature will not change for a while, and I will be looking at E equals MLV for step 4. Okay, so that'll be 80 times 300, or sorry, 2,260. Okay. All right, so we're looking at 180,800 for that. Okay, and then at the end of that step, I have steam at 100 degrees Celsius. If I keep heating it, the steam's temperature will increase. It's another diagonal part of our heating curve. So that's E equals mc delta T, 80 grams times the heat capacity of steam, 2.02, times the temperature change. I'm going from 100 to 160. So the temperature change is 60. Okay, it's 9,696 joules. All right, so if I add all of those together, I should get 250,507.2 joules. Okay, that's as long as that type of question can possibly be. Okay, are we starting to feel a little bit more confident about how to do these? Okay, remember, on a unit exam, probably be a 3-step question. Okay, it won't be 5, just takes too long. Okay, let's have you finish those ones up or as close to being finished as you can on those. And then tomorrow, we're probably going to do like a quick activity with some ice and water and stuff like that. It won't be anything you have to hand in for marks or anything like that, but we'll try and calculate or measure exactly what the latent heat of ice is. Okay, we'll do a little experiment to test that tomorrow. All right. Okay, keep working on those.